Questions about anything from last time? Anything? Well, this I'm going to finish off discussion of uniform continuity today before starting to talk about monotone functions, which turn out to be pretty interesting once you gain the basic facts about real numbers. Were there any questions? Okay, so at the end of last time I stated this theorem, the continuous extension theorem. It had to do with a uniformly continuous function on an open interval. And if f is uniformly continuous on an open interval, then the theorem states that it extends to the endpoints in such a way to make it continuous. So that means that extends to the closed interval AB in such a way that it's continuous. So that just means you can give it values at A and B, that sort of are the obvious values they should be just to make that happen. Although the proof isn't going to make it so obvious what those values should be, you have to think about it. So in such a way that f is continuous. And of course, if a function is continuous on a closed interval, it's uniformly continuous there too. So kind of a remark, if it's continuous on a closed interval, then it's uniformly continuous there. That was the topic of last lecture. Okay, so let me demonstrate why this is true. It's kind of a nice argument. So why? I'll do the A side. So let xn be a sequence in AB such that xn tends to A. I guess we put sequences in bracket. Well, convergent sequences are Cauchy sequences. We know that. Convergent sequences are Cauchy. So I'm going to I want to show that I'm going to show that f of xn is Cauchy. So we will show that the sequence f of xn is also Cauchy. We don't know what it converges to, but being Cauchy means it does converge to something. So it's also Cauchy. Let's see how we do that. Well, whenever you're going to show something is Cauchy, step one is to say let epsilon be bigger than 0. And so what are we going to do with that? Well, because xn is Cauchy, means I can find So that means there's an n, capital N, such that xn minus xm absolute value is less than epsilon when either of those n or m's are bigger than m. Okay, so what is that? But when you think about that, the aha moment is f is uniformly continuous. And so So here's where you realize what the key is here. F is uniformly continuous, so there would be a delta yeah, so this is the thing. I need to let the delta be the epsilon in this case. Let's see, such that yeah, so here's I just got hung up because I'm thinking of okay, I skipped something. I should have kept my eyes on my notes. I'm doing something out of order. It doesn't matter what order I do it in, but now I have to go back and fill something in. F is uniformly continuous. So there exists a delta such that xn minus xm less than delta implies f of xn minus f of xm is less than epsilon. Okay. Now here's what I should have done. When I look at this now, I let my epsilon be bigger than 0 back there. And here's what I should have done. I should have, now I can go back and I need to take this epsilon to be equal to delta. So xn is Cauchy, meaning give me a delta bigger than 0. I can find an n such that that would be less than delta. And now I'm going to use that delta to be the thing that comes from uniform continuity. Okay. So I should have had that sentence before I did my sentence with the x's n's. Then it would have made more sense. So what we get from the previous thing is that f of xn minus f of xm is less than epsilon when n, m are bigger than capital N. And that's exactly what it means to be Cauchy. F of xn is a Cauchy sequence. And we know a sequence converges if and only if it's Cauchy. So it converges to something. So limit as n goes to infinity, f of xn is equal to something. Let's call it capital A. And that, of course, is the value we need to give f at little a. Now, to show that a is the limit of f, I need to show that all the sequences that converge to next, I need to show that for every sequence, I'll call this sequence u sub n, with u sub n in the interval from a to b, and the u sub n goes to a, that the limit as n goes to infinity of f of un is the same thing, equals that same a. I just showed you that that series would converge, but I didn't show you what it converges, that it converges to the same a. That turns out to be easy. So it's kind of easy. Suppose it's not. Suppose it's equal to something. Suppose we know it exists. Because I can let the un be equal to the xn and repeat that argument. So we know it exists. Let's say it's b f of un equals b. We know that exists. Now here's a classic analysis type trick to do. A minus b. I want to show that that's really can be made arbitrarily small, so it has to be 0. Well, the f of xn's are getting close to a, so I'll put a minus f of xn there. I'll make this a different color so you realize I'm adding and subtracting. So minus f of xn. If I subtract that, I'd have to add it. And if you think about the other side, the f of un's are getting close to b. So, get a different color here. I'll subtract f of un. Let's see, yeah. I'll subtract it first, and then I'll add it back. And then I have minus b left over. And you realize now I've written that a minus b as the sum of 3 really small things. Okay, so this is less than or equal to a minus f of xn. And then this is f of xn minus f of un. That's small for a different reason. And this other one is small because the f of un's are tending to b. So when you start thinking about each term, this term goes to 0 because as the n goes to infinity. And the only one we have to think about is the middle one. Okay, so let's think about the middle one. The way to think about that is that the xn and the un's are both tending to a. So they're also getting close together. And if they get close together, then I can use uniform continuity to make that as small as I want. So if somebody made you explain it in gory detail, you'd say that, oh, xn tends to a and un tends to a. So xn minus un tends to 0. So given an epsilon bigger than 0, then I can use uniform continuity. So there is a delta bigger than 0, such that f of xn minus f of un is less than the epsilon when xn minus un is less than delta. That's by uniform continuity. Okay, and because xn minus un goes to 0, I can certainly make that happen. So xn minus un tends to 0 as n goes to infinity. So there is a capital N such that that happens, such that xn minus un is less than that given delta when n is bigger than capital N. So that middle thing goes to 0 too. Middle term goes to 0 too. And so now we conclude that a minus b has to be 0. So a equals b. Sorry, what did I do? And now we've shown that any sequence that tends to little a, that the values tend to capital A. So that means, so we've shown that f of un tends to A for all sequences. E that tend to A. Tend to little a. And that's the sequential version of continuity. So f is continuous up to A. If we define the value there to be capital A. And of course, it's similar for the other endpoint. I won't repeat it. Questions about that? That's kind of a place where the facts about Cauchy sequences are critical. I couldn't show it converges, but I can show that it's Cauchy. And that's the key to getting your foot in the door. Well, today's subject is in section 5.6 is about when you start thinking about monotone functions and continuous functions at the same time. So, monotone functions and how being continuous interacts with them. So that's the subject of 5.6. We're skipping 5.5. Monotone functions and continuity. Well, annoying thing about monotone functions is there's two kinds, increasing and decreasing. And the arguments are exactly the same for both. And so I don't want to repeat everything I do. I'm only going to think about the increasing cases. Let's see, only do the increasing case which means that x1 less than x2 would imply that f of x1 increasing means less than or equal to here. Strictly increasing would mean there'd be a strict inequality. Okay, so I'm only going to do that. The decreasing case is similar. And all books will be lazy and say, oh, they'd probably make them an exercise to write out the details of doing it when everything's going the other way. Okay, so I mean, when you try to draw the worst increasing function you can think of, it's surprisingly difficult. Oh, let me draw one that's at least got some jumps. The thing about them is jumps are possible. I want to do it on a closed interval. So there'd be a value here. Let me make it blue. Okay, going to increase for a while. And then there might be a jump. Oops, and who knows what the value is in between. It might be in the middle of the jump. And then it would continue increasing. Maybe this one would have a limit to the left, and then it would continue increasing. And maybe this one has a limit on this side. Oops, I'm going to run out of space. I better make a smaller jump. Etc. And now I'll make the, and let's see, there could be a jump at the end. Okay, let's do some dots here. So there's some, oh, darn it, sorry. Trying to do here. Okay, and you're going to ask yourself, how many jumps can I make? I could split each of those in half and make jumps in the middle. I could start doing that over and over again and get like a huge number of jumps. And the question is, what if a great genius sits down and tries to come up with a monotone function that has infinitely many jumps? And then the big question is, how big is the infinite? Is it countable or is it uncountable? And people like Cantor were already thinking about that. Cantor has this famous function called the middle third Cantor function. And he very cleverly came up with a monotone increasing function that had countably infinitely many jumps. Of course, they get really small. Some of those jumps are, and in fact, they get infinitesimally small. But there's only countably many of them. It's hard to believe, but I'm going to explain it to you in the next day or two, what Cantor did. It's brilliant. It's a mind-blowing function because its derivative exists almost everywhere. That's a word that means something. Two words that mean something. The derivative exists almost everywhere and is zero. And yet it's an increasing, it increases from something to something, even though its derivative is zero almost everywhere. And it has infinitely many jump points. So that's a mind-blowing thing. But before we start blowing our mind, let's think about those jumps. There's an easy fact to begin with. So here's some easy facts. I'm going to take a C here, and let's take a C where there's a jump. Oh, I'm going to make this C be where that jump is. facts are the limit as x tends to c from the minus side of f of x exists and is equal to, let's think about it, that's the soup side. That's the soup of f of x for x less than c. And on the right-hand side, think about that, I slide down from the, if I'm sliding down from the right-hand side, then that limit would be the minimum, so the inf. So from the right-hand side, the c plus side, that would slide down and be the inf. And notice that everything in the top set is bigger than or equal to everything in the bottom set. So that that thing on the top is going to be less than or equal to the thing on the bottom. So note, everything in the top set that's the soup set, is greater than or equal to everything in the inf set. So the top thing is greater than or equal to the bottom thing. So the limit as x goes to c from the minus side, what? I have it backwards. Everything in the inf set, that's to the right-hand side, is greater or equal to everything in the soup set, because that's the left-hand side. So the limit as x goes to c minus is less than or equal to the limit as x goes to c from the plus side. That's an important thing to know. Well, we learned some facts. Once we have this, I guess I need to demonstrate this easy fact. Let's see. Let's think about, let me do why one of them is true. So why the limit as x goes to c from the minus side, f of x is equal to the soup as x less than c of f of x. Well, this is where that epsilon definition of soup becomes essential. Remember back when when we defined soup, we messed around with this sort of complicated way of thinking about it, and this is why. So I'm going to let epsilon be bigger than 0. And remember the characteristic property of soups was we know there is an x1, let's say, x1 with x1 less than c such that, let's see, let's call this thing, this number, whatever it is, let's call this capital S for soup. So since that's the soup, we know there's an x1 in there, so that's less than S minus epsilon. I'm sorry, greater than. Right, that's the soup. So if there was no such thing, then the soup would be less. If there's no such x1, the soup would be would be less than x minus epsilon. And remember, the soup is the least upper bound. Therefore, there's got to be one. Otherwise, the soup would be smaller. And that epsilon is exactly the epsilon. See, what I need a delta now. How am I going to get a delta? So I've got S here and an S minus epsilon here and an x1 stuck in here somewhere. And remember, F is increasing. And so where could it be between, when you're going from x1 and above, you realize, aha, I'm stuck in an interval. F would be stuck in an interval. So the aha, if I have an x, let me get a different color x here. If I put an x in there, if x1 less than x less than s, then let's see, then f of x1 would be less than f of x. And remember the soup, I'm sorry, what am I doing here? Oh, this is stupid. We know there's an x1 with x1 less than c such that, okay, I'm being dumb. Okay, here's c. Here's x1. Now I'm starting to make sense. If my x is in here, then I'd have x1 less than x is less than c. And I'd have f of x1 is less than f of x. And remember, s is the soup. So this thing is less than s because s is the soup of those things. In other words, f of x is squeezed in there. So if you ask yourself, what delta should I pick for my limit? So it's obvious. Pick delta to be equal to x minus x1. And that gives me that the f of x minus the soup is less than the epsilon. So check. That limit is what I said it is. Yeah, you really need the increasing thing there to be able to because once you have x1 squeezed in there, all the x's to the right also have to be squeezed in there. So that's the way to think about it. Okay, and of course the other side is similar. X bigger than c. Similar, so I won't repeat it. Just reverse the inequalities, basically. Well, we know that when we studied continuity, we had a sequential definition and we had a limit from the left and right definition. So a fact, f is continuous at c, is equivalent to those two limits being the same. Of course, they have to be equal to f of c. And so a consequence of that a monotone function is continuous at C if and only if those jump things are the same. Let's see. A monotone, or let's say increasing, is continuous. An increasing function f continuous at C. If and only if those two limits, left and right limits, exist and are equal, and in our case, that means that the sup of the f of x for x less than c is equal to the inf of f of x for x greater than c. And so the only place where it can jump is where those two things are strictly different. Say, we'll call C a jump point. So C is a jump point if those two things are different. So let's see which one is, the inf one is the big one. And so if they're unequal, that would mean that the inf one is strictly bigger than the sup one. And we call that the J of C is the jump value. Oops, I didn't quite. J of C is the difference of those things. So the jump is going to be the inf minus the sup. And that's going to be something strictly positive. And f is continuous where the jump is 0. F is continuous where the jump function is 0. Remark. Questions about that? Okay, so this is the kind of the coolest fact we're going to demonstrate since Cantor's theorem. So, coolest thing since we showed Cantor's proof that the cardinality of the real numbers is strictly bigger than the cardinality of the natural numbers, meaning there's no onto map from the natural numbers to the real numbers. So that means there's orders of infinity. Well, so the coolest thing is this theorem. An increasing function can have only countably many jumps. An increasing function. It can be a closed interval or an open interval, I don't care. My C's have always been inside, so I'll take an open one. An increasing function on, oh, I better make it closed so it doesn't blow up. Can have at most countably infinite many jumps. So it can be finite or countably infinite, okay, meaning in one-to-one correspondence with the positive integers. And the proof is, of course, fiendishly clever. When you somebody locked you in a room and said you can't come out until you show this, you'd eventually think of this, but it'd take a while. Maybe. So here's the demonstration. Let's think of, here's why. Let's take finitely many jump points. Say A is less than or equal to x1 is less than x2 is less than, I'm only going to take finitely many. X sub n, that'd be less than or equal to b, are jump points. I didn't say what a jump point at A or B was all about, but you could guess that definition and fill it in if you wanted to. Say those things are finitely many jump points. I just pick, there might be a lot more. I'm picking finitely many. And I've ordered them to be like that. So it's important to note there might be more, a lot more. Okay, here's one of the dirty tricks the book does to you. In all those pictures you drew, you saw that, oh, I could take a flashlight and make the shadow on the y-axis, and I'd see that the add of all the jumps has to be less than the jump, the total jump. So if I add up all the jumps, the sum of all the jumps, xk, as k equals 1 to capital N, has to be less than f of b minus f of a. And rather than explain why that's true, the book says why. And you'd have to sit down and think for a while. In fact, I did. Let's try to prod my memory about why that's true. Anybody venture a guess? What's it?
Is this less than or equal to, or just less than?
Yeah, less than or equal to. Let's see, did you have an idea? Is that your idea too? Oh, okay. Yeah, sorry about that. But it could be less, as my pictures demonstrated. Okay, so let's see. It's kind of like the telescoping series business. If I have, let's have a capital A and a B and Y1, Y2 out to Y n, capital N, then B minus A would be the sum of all the differences. So it would be B minus Yn plus Yn minus 1 plus etc. plus Y2 minus Y1 plus Y1 minus A. That's something that's obvious because it's a telescoping sum trick. And now if you think about a jump, okay, I'm going to have a jump here. Let's make a jump at xk. To the left, it looks like that. And then to the right, it looks like that. And there's a jump. And I don't know what the value at the xk is. And I kind of want to get points like in the picture there with the capital A and the capital B. Any ideas about how I could get points like that? They're not going to be the xk's, because the xk's has jumps. That's bugging me. Anything come to mind? Yeah.
Maybe something with the supreme.
Yeah, I got soups and imps. Which means, yeah, so exactly. But I've got my next jump is going to be somewhere over here, maybe, xk minus 1. And I have another jump over here, xk plus 1. And I don't want to choose points that are past those other jumps. So your idea of thinking about the soup and the inf business is I can take the epsilon to be small enough, like I did in that demonstration, and I'll get, let's call it a UK here, and a UK plus 1 here. I guess let me call that a little UK and a capital UK. Then when you think about it, that UK, because of the soup and the inf business, f of UK minus f of little UK is strictly bigger than the jump. And so if I add all those things up, let's see what I'm going to do. So the sum of all the jumps, as k goes from 1 to n, that would be strictly less than, let's say it's not strictly less than, if this function was constant, for example, it could be equal to. So this would be greater than or equal to the sum of the f of UK's minus the f of little UK's and that picture above of the strictly increasing thing means that this would be greater than or equal to f of b minus f of a. Doggone it. What? The jump is left. Yes. Why do I do that? Okay, I'll let you think.